When iron is exposed to water and oxygen, it undergoes a chemical change, resulting in the formation of iron oxide, rust, and hydrogen gas. Here is the skeletal equation. Fe plus H2O yields Fe3O4 plus H2. But there's a problem. We have one iron atom on the left, but 3 on the right, and one oxygen atom on the left compared to 4 on the right. Because the atom counts are unequal, this equation does not yet satisfy the law of conservation of mass, which states that atoms cannot be created or destroyed during a chemical reaction. To make the written equation match the physical reality, we must balance it. We can do this systematically using a 7-step method to ensure the number of atoms for each element is identical on both sides. Step 1 is to draw boxes around each formula in the equation. This is a reminder of what we can and cannot change. While balancing, never alter the subscripts inside these boxes. Changing a number inside the box changes the identity of the substance itself. Instead, we can only add whole numbers, called coefficients, to the front of the boxes to multiply the total number of molecules. Step 2 is to take inventory. By listing the number of atoms for each element on the reactant side and the product side, we can see exactly where the imbalances are, specifically with the iron and the oxygen. The goal is to reach a state where every element has the same count in both columns. Step 3 is to pick a starting point, usually the compound with the most atoms, like Fe3O4. We'll start by balancing the oxygen atoms, since we have 4 on the right and only 1 on the left. By placing a coefficient of 4 in front of the water molecule on the left, we now have 4 oxygen atoms on both sides. Step 4 is to check for side effects. Adding that coefficient multiplied the hydrogen atoms as well. 4 molecules of H2O mean we now have 8 hydrogen atoms on the reactant side. To balance this, we move to the product side and place a 4 in front of the H2 gas. Now, the hydrogen counts match at 8 each. This iterative approach is called the hit and trial method. We continue making adjustments, element by element, until the counts for the entire equation are equal. Step 5 is to address any remaining elements. Only iron remains unbalanced, with 1 atom on the left and 3 on the right. We place a coefficient of 3 in front of the iron, bringing that count to 3. Step 6 is the final check. We verify the totals one last time: 3 iron, 8 hydrogen, and 4 oxygen atoms on each side. The inventory is now perfectly identical. To complete the model, step 7 is to include the physical state symbols for each substance. We use S for solid, L for liquid, G for gas, and AQ for aqueous solutions. Adding these provides the necessary context for how the reaction actually occurs. Note that in this reaction, water is marked with a G because it is used in the form of steam to react with the iron. The equation is now balanced and includes all relevant physical information, making it a complete representation of the reaction. The final balanced equation reads 3FeSS plus 4H2OG yields Fe3O4SS plus 4H2G. By aligning these quantities, we have demonstrated that mass is conserved throughout the process, fulfilling the requirements of the law of conservation of mass. Now that you've seen the steps, try applying them to this reaction. Magnesium plus oxygen yields magnesium oxide. This 7-step method provides a foundational logic for balancing fundamental equations, a systematic process you can apply as you move toward more complex